This video covers our section on exponential equations and growth from our chapter on growth and mathematical modeling. This section will cover exponential growth, and it'll talk a little bit about our three types of growth: linear, quadratic, and exponential, and we're going to kind of compare and contrast them a little bit as well, which is our first objective. But first, let's talk about what is exponential growth, sometimes called compound growth. We're going to use an example of compound interest, which is a very common application of exponential growth. So let's say we invest $1,000 into an account that earns 10% interest compounded annually. What this means is in the first year, you're going to earn 10% of the $1,000 you invested, which is $100. You add that onto your $1,000, and now you have $1,100 in the account. And the second year, you earn 10% of that $1,100, which is $110, right? So notice first we earned 100, now we're earning 110. If you add that on to what you had, you now have $1,210 in the account. And this is going to keep going on, right? We'll earn 10% of that, which will be even more than $110. So what's happening is we're earning interest not only on the original $1,000, but also all the previous interest that we've accumulated, and this is going to grow faster and faster each time. This is what we call compound growth or compound interest in this case, and it's characterized by growth on top of previous growth. So if we summarize our three types of growth here, linear growth was a quantity that changes by the same constant amount for each unit of time. Quadratic growth, remember our parabolas, it involves a quantity that either increases, reaches a maximum, and then decreases, or the opposite, it decreases, reaches a minimum, and then increases. And then our new type of growth, exponential growth, it's a quantity that changes by the same percentage or factor for each unit of time. So we're going to take a look at three little examples here, and we're going to try to determine what type of growth does this describe and how do we know. So our first example is in the year 2009, there were 432 cases of violent crime per 100,000 people in the US, and this number was decreasing by 26 per year. They give us a piece of data here. 2009, there were 432 cases. That's kind of our starting value. Don't be thrown off by the 100,000, by the way, because that's just how the statistic is reported, right? 432 cases per 100,000 people. So we actually don't need the 100,000, but we have the starting value of 432, and then we have the rate of change, which is decreasing by 26 per year. So our rate of change is negative 26, right? Because it's decreasing, so it's negative. And the point here is this is a constant rate. Right? We have a constant rate. Each year we're just going to lose 26 cases over and over. So this is a constant rate, which means we have a linear growth scenario, right? As long as you have a constant rate of change, you know you have a linear growth scenario. We can model that with the linear equation and y equals mx plus b, and then make some predictions. So that's what we're looking for. What type of growth, what's changing, and how is it changing? And if it's constant, linear growth scenario. Okay, so that's our first example. Let's take a look at the second one. A post on social media goes viral and the number of likes per day increases rapidly. After a few days, the popularity levels off and the number of likes per day starts to fall. Okay, so this is interesting because we don't have any numbers at all, right? We're just kind of describing it, but you can picture it. The likes per day increase rapidly, right? They must reach some maximum value because it says it levels off and then they start to fall again. So we kind of have this increase, reach a maximum, decrease scenario. This describes a parabola opening downwards, right? Increase, reach a maximum, decrease. So this fits a quadratic growth scenario. Not a lot of details here. Usually we don't build our own quadratic equations because it's a little bit complicated. There are ways to do it with technology. With quadratic models, often they just give it to us. They say this equation models this scenario. But you can see that this wouldn't fit any of the others, right? It's not growing at a constant rate, and it's not growing by a percentage or factor. So up and down or down and up, that is your quadratic growth scenario. And then lastly, it says the average four-door sedan costs $21,000 today, and due to inflation, that cost would increase by 2.1% each year. So notice we have our starting piece of information. Our fixed value is the $21,000 today, or initial value that is, and it's increasing, but instead of increasing by a constant rate, it's increasing by a percent each year. So like our first example, it's going to first be 2.1% of 21,000, then you add that on, then you take 2.1% of that, and you end up with growth on top of growth. So this describes a compound growth scenario. It's because we have an increase by a percentage, right? Each year we earn 2.1%, which means the actual growth is increasing faster and faster each time. Okay, so 3 quick examples, and you kind of know what to look for if you want to figure out if you have linear, exponential, or quadratic growth. This will be definitely important when like the final exam rolls around, or let's say a chapter test or a quiz. When you put all these growth scenarios together, the problems rarely say, hey, it's this type of growth, so investigate this. You'll have a scenario and you'll have to kind of determine what type of growth, what type of equation would fit this, what type of techniques do I need to use. Moving on to our second objective, we're actually going to look at some exponential equations and do some modeling. Our general form of an exponential growth equation will be this: a equals p times 1 plus r to the t power. In this equation, p is the initial value, which when we talk about interest, we'll often call it the principal. R is the growth rate, which will be given as a percent. Just make sure when you plug it in, you convert it to a decimal first. T is the amount of time, often given in years. And A is the future value. That is the total amount of whatever you're measuring after T time units have passed. Notice there are 4 variables in this equation, and at any given time, you could be given 3 and asked to find the 4th. Solving for A and P is pretty easy, it just requires basic algebra skills. Solving for R means you have to get rid of the T power, which requires what we call a root property, which is some slightly advanced but pretty simple to use with the calculator algebra techniques. We'll look at an example of that coming up. And then solving for T requires that we get a variable out of the exponent position, which is going to require a logarithm, which we'll look at in our last objective. Let's go ahead and look at this first example. It says in 2015, the population of Japan was 127 million and had a growth rate of negative 0.1% each year. Use this information to create an exponential model and estimate the population of Japan in the year 2030. So we have a growth rate, which is a percentage, so we know it's exponential growth. However, it is a negative growth rate, which is interesting because so far we've talked about exponential growth as something growing faster and faster. If you have a negative growth rate, that means it's decreasing. And for exponential equations, sometimes we call it exponential decay. And this is the case, or at least in 2015 it was the case, that Japan's population was actually decreasing. So it's not a big deal. All we're going to do is when we plug in our R value, obviously it's going to be a negative value, and the model will then decrease in population as time increases. So let's start with our general form of our equation again, which was the A equals P times 1 plus R to the T. So A is our future value, and it looks like that's what we're after in this problem, right? It says use this information to create a model and estimate the population in the year 2030. So what is the population in the future? That is an A value. So let's go ahead and leave A alone for now, because that's what we're going to be looking for. P is the initial population, which is 127 million. 1 plus R, we're going to end up with 1 minus, and then be careful here. We want to, this is a percent. We never do arithmetic with percents. We convert them to decimals or fractions first. So percent to a decimal, you move the decimal twice to the left. That's going to give us a 0.001 as our R. And then T is the amount of time. Now, we don't want to plug in 2030 here, right? Our starting year was 2015. 2030 is 15 years later. So we're going to plug in 15 here. And I usually like to make a little note here. This is just 2030 minus 2015. Right, we figured out how many years have passed from our starting to the future that we're looking for. And this is what we need to calculate. Now, luckily, we have calculators that can do this arithmetic because we don't want to raise something to the 15th power by hand. But if you plug this into the calculator, pretty much like you see it, you can do an extra step to do the 1 minus 0.001 if you want. But the calculator will do this all together. To raise things to the 15th power, we'll probably make a separate video talking about how to do some stuff like this on the calculator, but there should be like a caret or chevron button that raises u to the power. And when I did this, we'll go ahead and round this to the nearest whole number. So I'll use a squiggly equals. This is approximately equal to 125. These are millions, so 125 million. Okay, so it was 127 million, right, in 2015. 15 years later, if this growth rate stays the same, it's going to decrease to 125 million according to our data. Okay, so a pretty straightforward application of this exponential growth equation. Often, finding A is the easiest case, right? Because you have P, R, and T, you plug it all in. You don't have to do any algebra at all. It's basically just calculator work. Let's look at another example here, number 2. It says a population of trout were seeded into a lake and increased by 60% per year. After 4 years, there were 1,500 trout in the lake. Use this information to create an exponential model and find the size of the initial population that was introduced to the lake. So we have this lake, we put some trout in there, it grew, and 4 years later, there were 1,500 trout. We're trying to figure out how many trout were put in there in the first place, the initial population. In our formula, that's going to be P. So we're looking for P, and we actually know what A is, right? It says 4 years after there were 1,500 trout, so our A value is 1,500. Let's go ahead and just plug into the equation, starting with A, we have 1,500. That is our future value. We're looking for the initial population, which is P. Population and compound interest, by the way, are the two most common applications of exponential growth. So this is our population example. Our growth rate, it is increasing this time, so it's going to be positive. 60%, remember as a decimal, move it twice to the left, we'll get 0.6. So 1 plus 0.6. And T is just 4 years. So we want to solve this for P. I recommend that you don't enter anything into the calculator until the very last step, because often the intermediate steps will have some kind of rounding involved, and that's going to introduce error. So we try not to have any error until the very last step. So what I'm going to do is I'm going to isolate P here, right? We want to solve for P. This is P times this 1 plus 0.6 to the 4th power is a number. We don't care what it is yet, but it is a number. So if you want to get P by itself, you just need to divide by that number. And you could simplify this to 1.6 if you wanted, but I'm just going to save ourselves some steps. So these cancel out. We get P equals, and whatever the result of this division is, I'll go ahead and simplify it here, 1.6 to the 4th power. That will be our P value. Okay, so we got P by itself. Now we're ready to enter this into the calculator, and we'll go ahead and again round this to the nearest whole number. Just be careful when you insert things like this into the calculator. Often it's a good idea to put your numerator and denominator in parentheses separately, just so the calculator does everything in the order you want it to. And I'm getting about 228.8, so let's call that 229. And what was our units? Raw numbers, right? Yeah, so 229 trout in this case. So 229 trout. Okay, so according to our model here, we started with about 229 trout in the lake. It grew by 60% per year. 4 years later, there were 1,500. So this is an example of solving for P, the principal or present value, or initial value. And notice the algebra was pretty simple, right? All we did was divide both sides by this number, and just make sure that you try to wait until the very last step until you enter things into the calculator. One more example here. Suppose your parents placed $5,000 into a college savings account when you were born, and when you turned 18, the account had grown to $22,000. Assuming the interest was compounded annually, what was the interest rate on the account? So it looks like this time we have the starting value, which since this is money, we'll call it the principal. So we started with $5,000, the principal. It grew by some amount. 18 years later, it had grown to $22,000, which is the future value. So we have the principal, we have the future value, we have the amount of time, 18 years. We're looking for R, the interest rate. So let's go ahead and set this up, starting with A, our future value, which is the 22,000. Equals P, our principal, which in this case is 5,000. We have 1 plus R. Remember, R is what we're after the growth rate here. and this is going to be raised to the 18th power because it was 18 years after. We want to solve this for r. So if we want to solve for r, we have to get rid of this 18th power, which is going to require us taking an 18th root. In order to do that, though, we first want to isolate this 1 plus r piece. So our very first step should be to get rid of the 5,000, and because it's being multiplied by the quantity 1 plus r to the 18th, we need to undo that multiplication by dividing both sides by 5,000. So that goes away. We get just our 1 plus r to the 18th, which is what we wanted. Now over here, sometimes this divides nicely, sometimes it doesn't. Just to be safe, remember, we don't want any rounding going on. Let's just leave this alone until the very last step, and then we'll bust out our calculator and do our estimation at the very end, or our approximation. But in order to save ourselves a lot of writing, a lot of messiness, I like to just cancel out these zeros, right? We're basically just reducing this fraction, dividing both sides by 1,000. So to simplify this side, let's just call it 22 over 5 for now. Same thing as 22,000 over 5,000, but easier to write. Okay, so we've isolated the piece with the power. We now need to get rid of the power. And just like you would get rid of something being squared, you take the square root. Something is being raised to the third power, you take the third root. If something's raised to the 18th power, we're literally going to take the 18th root. And this is what we call the root property, because we're going to apply an 18th root to this whole side. And in algebra, whatever you do to one side, you have to do the same thing to the other side. So we're actually going to apply the 18th root to both sides of the equation. Now we're doing it over here because the 18th power and the 18th root, they undo each other. And we're left with 1 plus r, which we don't even need the parentheses for anymore. Now over here, 18th root of 22 over 5, that's asking us what number, when you raise it to the 18th power, gives you 22 over 5. I have no idea. Luckily, the calculator will take care of that for us. And it's going to be kind of a messy number. So again, wait till the end to enter this. Our last step, though, to get r by itself is we need to get rid of this 1. So we subtract 1 from both sides, and this is actually what we want to enter into the calculator. It'll be the 18th root of 22 over 5, and then minus 1. Make sure that minus 1 is on the outside of the root here. And that will be our r. Okay, so in the calculator, we will enter this. And again, this is a slightly complex thing to do on the calculator, so we'll probably have a separate video. But there is a function on the calculator to take pretty much any type of root you want. If you put it all together, let's go ahead and, I like to do 3 decimal places here when we do our rounding. I'll tell you why in 1 second. So we would get 0.0, let's see, 0.85, we'll call it 0.86 because there's a 7 after it. Okay, so I rounded it to 3 decimal places. Because this is a growth rate, we often like to give our final answer as a percent. Oops. So, sorry about that. So if you have a decimal and you want a percent, you move the decimal twice to the right. This is going to give us about 8.6%. Okay. So keep in mind when you go to round your answer as a percent, you always want 2 extra decimal places. So maybe this problem said, give us a percent, round it to the nearest 10th. So instead of rounding our initial answer to the nearest 10th, I took 2 extra decimal places, right? 3 decimal places, because I knew I had to move it twice to the right to make it a percent. So just kind of keep that in mind when you get a raw decimal and you want a percent at the end, just take 2 extra decimal places. So this was our example of what we call the root property. And remember, anytime you want to get r, the growth rate, it's going to be raised to a power. You have to undo that power by applying the same exact type of root you have. So if this was the 28th power, we would have taken the 28th root. So make sure you do it to both sides and try to wait to the very last step, right? Once you do the algebra and get r by itself, none of this is simplified or approximated until this step. At this step, I enter it into the calculator. That way, my only error occurs at this step, and there's not kind of some compound error that adds up. Okay, so that's the examples so far of finding A, P, and R, which aren't too bad. Finding T is going to require some new algebra using what we call logarithms. So let's talk about that here in Objective 3. A logarithm is the inverse of an exponential. So for example, if you have this equation 2 to the third equals 8, we could kind of rewrite this as a logarithmic equation in the following form. Log base 2 of 8 equals 3. What this is saying is this log base 2 of 8, This is the power that you raise 2 to in order to get 8. Okay, so it's just a way of undoing an exponential. Now this is important because you might have an equation like this, 2 to the x equals 7. To solve this equation, you're trying to figure out what power do we raise 2 to in order to get 7. And there is no clean number, right? 2 to the second power is 4, 2 to the third power is 8. So that means that the power we raise it to get 7 has to be something between 2 and 3, and we're going to need a calculator to chip away at it. So in general, we're going to use logarithms because they undo exponentials. And we're going to use a couple main ideas of logarithms. This is a much bigger topic that we could investigate. Luckily, we don't need to talk too much about logarithms. We're going to use them for this very specific example. First of all, we're going to use what we call common logarithm, which basically means we're going to ignore the base. Log base 10 is our common logarithm, and because it's common, we often write it without the base. And it actually doesn't matter what type of logarithm you use. I know it's kind of weird, but we're just going to write log, okay? So in the back of our heads, keep in mind log is log base 10, but the calculator is not going to worry about that. We're just going to write log. And we're going to use this one property called the exponent property of logarithms. We're going to apply a logarithm to both sides, and what's going to happen is when you have a logarithm of a number raised to a power, the logarithm function allows you to take that power, in this case the a, and pop it out in front of the logarithm, and it'll become multiplied by the log. So essentially, it helps us extract exponents from the exponent position. So let me just show you this quick example of how we do this. 2 to the x equals 7 is our equation. We want to get the x out of the exponent position, so we apply a logarithm to both sides. Remember, this is our kind of backbone of algebra. Whatever you do to one side, you do to the other. So we apply the logarithm to both sides, and on this side, we have log of 2 to the x. This is where we use the exponent property. We extract the x out of the exponent position, and we get x times the logarithm of 2. Now in this step here, I know it looks weird, but log of 2 is just a number, and log of 7 is just a number. So we have x times this number, and if we want to isolate x, we can divide both sides by that log of 2. And so we get x equals the quotient here, log of 7 divided by log of 2. And again, always wait to the last step to do division. Now that to enter into the calculator. Now that we have x by itself, all we have to do is enter log of 7 divided by log of 2. Your calculator should have a nice little log button on it, so it's not too hard to find. And if you divide those two things, you get x is about equal to, this is rounded, 2.807. So you could check it. You could take 2, you could raise it to the 2.807 power, and you'll get approximately 7, right? You might get a little bit over, a little bit under, but basically 2 to this power will give you 7. So it's just a way of solving for unknown powers or powers that aren't like integers, whole numbers, right? We're getting weird kind of decimal powers, but it works. 2 to that power will give you about 7. Okay, so anytime you're looking for t in our example, right, because we have the exponent equation, if you're solving for t, which is the variable in the exponent, we're going to have to apply logarithm and use this property where we extract the power from the exponent position. It may sound complicated, but honestly, it's pretty straightforward after you see a couple examples. And as always, the calculator does all the dirty work anyway. So let's go ahead and look at this example and see if we can apply it. So suppose you invest $2,500 into an account earning 5.4% compounded annually, 5.4% interest compounded annually. Let's try that. And you want to save $20,000 for a down payment on a house. The question is, how long must you wait until you have that down payment? Let's think about what we have and what we're looking for, right? We have the starting investment, the principal. So here's P, 2,500. We have the growth rate, 5.4%. We have the future value. We want to have 20,000 in the future, so that's our future value. So we have A, P, and R, and we're looking for T. The question here is how long, which means we're looking for T, the time. So let's set this up in our equation, starting with A. Remember, A is 20,000. Equals P, our principal, which is 2,500, times 1 plus R. Our interest rate was 5.4% as a decimal. If we move that decimal twice to the left, we'll get 0.054. And we're looking for T. How long will this take? Okay, so just like last time, we want to isolate this piece with the T power. So we're actually going to start by moving the 2,500 to the other side. So I'm going to start by dividing both sides by 2,500. And again, I don't know if this divides evenly. I don't care. We're going to wait till the last step to do our approximation anyways. But to save us some writing, I like to cancel out some zeros. So 2 zeros for 2 zeros, just so we don't have to write all the zeros each time. We'll look at this as 200 over 25. It's technically the same thing. And over here, let's go ahead and add the 1 and the decimal. So we just get 1.054. That's a decimal there. Again, just to save us some writing. And this is to the t power. Okay, so we're just isolating the piece with the t power. This is, if you think about it, this is pretty much like that example 2 to the x equals 7. Instead, we have 1.054 to the t equals 200 over 25, but it's the same principle. We have a number raised to an unknown power. It equals some other number. We want to figure out what's the power. So this is where we apply the logarithm to both sides. So log of 200 over 25 will be equal to log of this whole thing. We don't actually need these parentheses here. I shouldn't have written them because we just have one number to the t power. So I'm just going to kind of drop those parentheses and write it like this. Right, same thing. So I'm just saying we're taking the logarithm of this whole quantity. And remember, this here is where we're going to apply that exponent property of log. We have log of something to a power, so that power is going to be extracted out in front of the logarithm. So let me just rewrite the left-hand side one more time. And over here, this t is going to come down out front, and we're going to have t times the log of just the 1.054. Okay, so that's why we introduced logarithms in the first place. We want to get that t out of the exponent position. And now that we've done it, these two logs are just numbers. So if you want to get t by itself, you undo the multiplication that's happening by division. So we're going to divide both sides by this number, this quantity, log of 1.054. And we get t is equal to the quotient of these logarithms. It may look messy, but all we need out of this is to use the calculator to approximate our t value. Okay, so remember, we're not doing any of this log stuff until this very end, which is, here we are at the very end pretty much. We're going to go ahead and round this. T is time, so again, let's go ahead and just pick the nearest whole number. So we'll do log of 200 over 25 divided by log of 1.054. And I'm getting about 39.5-ish, so let's just call it 40. 40 and years? What was, I forgot the context of our problem again. What was it? Yes, years. So we invest $2,500. We have an interest rate. We want to save $20,000 for a down payment. How long must you wait to have that down payment? Well, it's going to be about 40 years. Probably not a good deal in this case, right? You probably want to maybe invest more in the beginning or find an account that has a higher interest rate. But regardless, the point here is we have this scenario where we have our present value, our future value, our interest rate. We're looking for the variable t, which is the exponent. To find the exponent, we have to apply a logarithm. Don't forget that even you might have it in your head, okay, apply a logarithm if you're looking for t. Try not to do it at the beginning though. Remember, our first step is always simplify. So we want to get this piece here by itself. So we start by dividing both sides by the 2,500. Then we have this nice equation where we can apply the log to both sides, extract the variable down, and then divide by the logarithm. And at the very last step, that's when we enter it into the calculator. All right, one more example of this, and then we are done for this section. It says in 2015, the population of India was 1.225 billion and was growing at a rate of 1.2% each year. In what year will the population double? Notice the question again is in what year? So we know we're looking for t. We know we're going to apply a logarithm. We have our present value, our starting population, 1.225 billion. We have the growth rate. We don't have the future value, but we can figure it out, right? Because it says in what year will the population double? If we start at 1.225 and we want to double it, we'll just multiply that by 2. And if you multiply that by 2, you get 2.45. So we're looking for it to grow to our future value of 2.45. So that's our A value. Our principal, or sorry, our present value, initial value is 1.225 billion. We have our growth rate, which is 1.2%. Remember, as a decimal, move it twice to the left, we'll get 0.012. And we are looking for t. So this is pretty much going to go exactly like the last one. We want to start by getting rid of this 1.225, isolating the part that's being raised to the t power. And again, we'll save the approximation here until the end. So let's just write this again. Let's combine, let's do what I didn't do last time, drop the parentheses. We'll combine this, it'll be 1.012, and it's to the t power. This is our step where we apply the logarithm to both sides. I didn't save enough room, so sorry, I gotta write it real quick. Log of 2.45 divided by 1.225 will be equal to log of 1.012 to the t. So now we apply our exponent property. This t is going to be extracted out in front of the logarithm. So it'll be t times log of 1.012. And just rewriting this again. And this is the step where we want to solve for t, so we're just going to divide both sides by this log. Oops, what am I doing? Let's redo that. Sorry, we're dividing both sides by log of 1.012. Okay, this cancels out. We get t equals the quotient of these two logs. And because I don't want to write it again, let's go ahead and just throw it into the calculator now. But this is what we're throwing into the calculator, right? The quotient of these two logarithms. So it'll be log of 2.45 divided by 1.225 divided by logarithm of 1.012. These are years, so let's go ahead and do the nearest year, which I'm getting about 58. So, according to our model, in 58 years, India's population will double to the 2.45 billion. All right, so some new stuff here, some new equations. Most of it's pretty easy. The root property is not too hard to get used to. There's a little bit of new calculator stuff. This logarithm thing, again, it might be a little intimidating to look at, but if you do a couple and you think about it, we're really just using it for this one very specific purpose. We apply it to both sides and we extract the power from the exponent position. Entering in the calculator is very easy. There should be a log button right there in your face, so it's pretty easy to find and use, and then you get your answer, so not too bad. Hopefully this helps. Let me know if you have any questions, and thank you for watching.